Inside your joints, there exists a cell called a chondrocyte. It lives in solitary confinement, sealed within a tiny cave of its own making called a lacuna. Imagine being the sole architect and lifelong resident of a house you can never leave. This cell is responsible for creating and maintaining an enormous, complex structure around itself, your cartilage. Unlike most cells in your body, which are part of a bustling, interconnected community, the chondrocyte is profoundly alone. Its nearest neighbor is a vast distance away, separated by the very matrix it secretes, making communication almost impossible. This isolation is defined by a crucial absence: blood. Your cartilage is avascular, meaning it has no blood vessels woven through it. Think about a bustling city with highways and roads delivering supplies everywhere. That's a typical body tissue. Now, picture a remote outpost in a desert. Supplies don't arrive by truck. They are left at the edge of the desert and have to slowly, painstakingly seep through the sand to reach the center. That is how a chondrocyte gets its nutrients. Oxygen and glucose diffuse, molecule by molecule, through the dense matrix, a process that is extraordinarily slow and inefficient. Because there are no blood vessels, when you damage your cartilage, it doesn't bleed. And because it also lacks nerves, you don't immediately feel it. A cut on your skin triggers an instant, massive biological alarm. Bleeding summons platelets, inflammation calls in repair cells, and pain tells you something is wrong. A tear in your cartilage, however, is a silent event. The body's emergency response system is never activated. The chemical signals that scream for help are simply absent. It's an injury that happens in a territory the body's repair crews don't even know exists. The lonely chondrocytes near the damage do try to respond. They awaken from their quiet state and begin to divide, attempting to mount a repair. But their isolation works against them. Instead of spreading out to fill the gap, they form small, dense clusters, like tiny, disorganized families. Worse, these stressed cells don't produce the high-quality, durable hyaline cartilage that was there before. They create a mechanically inferior scar tissue called fibrocartilage. It's like patching a crack in a high-performance tire with chewing gum. It fills the hole, but it's destined to fail under pressure. Healthy cartilage is an engineering marvel. Its structure is a matrix of strong collagen fibers filled with a pressurized, waterlogged gel. This design is brilliant at absorbing shock and providing a near-frictionless surface for your bones to glide on. But its perfection is its weakness. The intricate basket weave arrangement of collagen fibers is laid down during development and is almost impossible to recreate. When that weave is torn, the chondrocyte, our trapped architect, has no ability to rethread the entire structure. The damage creates a weak point, and the immense mechanical forces of daily movement concentrate on that flaw, relentlessly grinding it wider. The pressurized gel inside the collagen weave is created by molecules called proteoglycans. The most important one is aggrecan, which has a structure like a bottle brush. These molecules are intensely hydrophilic. They are powerful water magnets. They pull water into the cartilage, swelling the tissue and creating the stiffness needed to resist compression. When the collagen network is torn, it's like snipping a hole in a balloon. The cage is broken. These vital proteoglycans wash out of the wound and the water follows. The cartilage literally deflates, losing its cushion and its ability to protect the bone. Ultimately, the chondrocyte is a maintenance worker trapped inside the very wall it's supposed to maintain. It has no access to a blood supply for new materials, no way to call for help from other cells, and no ability to move to the site of the damage. All it can do is secrete new matrix components into its immediate vicinity. But trying to fix a large structural tear by secreting molecules from a fixed position is like trying to rebuild a collapsed bridge by tossing single bricks from the riverbank. The scale of the damage is simply beyond the reach and resources of the isolated cell responsible for the repair.
Monotony has grown fast. Nearly 2,700 people have watched in the last few weeks, yet less than 0.03% are subscribed. It would mean a lot if you joined by hitting subscribe. And again, thanks for watching.